Hi, my name is John, and I'm working on formic acid dehydrogenation catalysis. So what we have here is formic acid, and here with formic acid, we can split formic acid into hydrogen and carbon dioxide. The great thing about formic acid is it's in room temperature, it's liquid, it's relatively non-toxic, and it's generally much safer than gaseous hydrogen, because in its liquid state it's much less flammable than gaseous hydrogen, and so it's a lot safer. The issue with formic acid is, in this case, is it's very stable, but it's so stable that we have to release the hydrogen out some way. And we do that using catalysts. So catalysts here drive the reaction to release our hydrogen. And so here in my syringe is our formic acid. And I'm just gonna inject it in. So we have catalysts already in the flask, and we're just gonna inject it. And, oops, sorry. And as you can see, the flask is already bubbling away, and it's it'll be constantly producing our hydrogen gas, and we collect the hydrogen gas up top there, and that's how our catalyst works. And this way we can store hydrogen safely as formic acid without having to transport it as high pressure hydrogen gas, we can transport it much easier across continents as formic acid. Well, with formic acid, you can imagine perhaps in 10-15 years, instead of loading your car with petrol, you load your car with formic acid, and in your car it converts it into hydrogen straight away. So we can completely phase out fossil fuels and replace it with hydrogen in the form of formic acid. Good question. I would say it's the synthesis of the catalyst itself, because with catalysts, our main challenges are trying to optimize the structure of it and trying to look for more economically efficient materials. Try to also minimize our reliance on really expensive rare earth metals, or such as or palladium and so forth. So yeah, that's probably the biggest challenge.